Good afternoon, everyone. I will do the introduction and thank you, Stafford from Tokyo, to join us. And let me tell you a story. When I was a computer science major freshman, just like everyone, I took a course called Introduction to Computer Science. That's the first time I know there's a thing called FPGA, and you can make your own CPU out of it. I was like, wow, that's dope. I'm gonna try this out. And then I Googled it, and an advertisement popped up. Thoracic FPGA board DE0-Nano equipped with the most high-end Cyclone 4 FPGA chip, costing around 3,000 New Taiwan dollar. That is about 100 US dollar. When I first powered it up, I followed the instructions on some random web page I searched and get a CPU running on it. It's called OpenRISC 1200, and the site is called OpenCore. To these days, things has changed. A new implementation called MOR1KX appeared, and a new generation of developer emerged. Let's welcome our brand new Nova in the OpenRISC world, Stafford Horne. So please.
OpenRISC.
Thank you.
And I'm also going to dive into the open source tools that help you build free silicon. My name is Stafford Horne. I live in Japan. Before that, I lived in China, and I grew up in California. I'm a software engineer at a bank, and I've been involved in open source programming since the year 2000, when I first heard about Linux. Since 2015, I've gotten involved in hardware and OpenRISC. Through OpenRISC, I'm now the maintainer of the Linux kernel port for OpenRISC, the debugger, EDB, the compiler, GCC, and also binutils, which has a linker and assembler. And I have 2 kids, so they keep me pretty busy, and I had a hard time to get time to put this presentation together. So, not OpenRISC, but RISC-V. How many people have heard of RISC-V? Well, it's a virtual conference. I can't see your hands, but I'm sure a few of you have heard about it. Now, RISC-V is from the year 2010 is when it was first introduced, and it's now gotten a little bit more popular. Now, RISC processors, or open source RISC processors, they started with OpenRISC. It's kind of the predecessor of RISC-V. It started in the year 2000 with the OpenRISC 1000 architecture, a open source RISC architecture, and the first implementation was the OR1200 CPU. It's a fully featured CPU that has an MMU, which means it can run very complicated operating systems with memory protection, and modern operating systems with memory protection. And it also has many different peripherals, such as a timer, power management, debug interface, interrupts, anything you need to run your latest modern day operating systems. The Linux port has been available upstream since 2010, and there are now other implementations as well, the MOR1KX and the Marocchino. Let's look a little bit deeper into the MOR1KX. The MOR1KX is kind of the latest OpenRISC architecture, which provides a very configurable architecture where you can swap out pipelines, disable components like the MMU, the floating point unit, and caches. And the pipelines available right now are a 5-stage pipeline called the cappuccino, we like coffee, and the espresso, a small 2-stage pipeline. It's available on GitHub. There's a link right there, OpenRISC/MOR1KX. And if we want to use this CPU in a design, you have to have a system on chip that integrates everything together. And in the open source world, we have a few different system on chip build systems. One of them is called FuseSOC, and the other is called Litex. We'll look a bit at FuseSOC later, but Litex, I'll just put one word, it's a Python-based build system, and you can actually build IP cores in Python. It's quite an interesting system. and I work on that as well. So if we deep dive into the MOR 1KX, we can see it looks similar to the OR 1200 architecture we showed before, where you have your timer, your interrupt, programmable interrupt controller, debug unit, and other peripherals. These, though, in the MOR 1KX can all be disabled or enabled to allow you to shrink down your design so that you can fit it on a smaller FPGA, or you can beef up your design and run a fully fledged operating system. This shows the 5-stage pipeline where you have your instruction fetch stage, your decoding. This is a combinational decode stage, and the decode execute is what registers the decoded operations for passing down to the execution stage. We have an ALU, or a load store unit, that can execute. Those are then, once done, registered in the execute control stage, and the output of those operations are then written back to the register file. Over on the left, we have the control module, which takes care of making sure if there are stalls that certain stages can be stalled, as to not continue to process incoming instruction streams. So that's it for the MOR 1KX. So why would you be interested in open source silicon or designing with open source tools? You might think to yourself, if you have an open source IP core, is it mature? Can I trust it? Is it as good as the vendor IP cores you might get from Xilinx? In terms of tools, you think the vendor tools are great. You have Vivado, Quartus. Those are great. They have 20 gigabytes of binaries, so that must mean they put a lot of work into it. Also, surely you can't do formal verification with open source tools. The IP cores you might get from Xilinx, you think they've been formally verified, or ARM cores you get and pay a lot of money for, they've been formally verified. And these open source tools definitely cannot do that. Those you might think, but those are probably not correct. So one of the benefits of the open source ecosystem is the wishbone bus. You've probably heard of it. It's used in RISC-V system on chips. It was introduced with Open Cores, which is the original home of OpenRISC, and it allows you to connect together your IP cores. Many open IP cores and vendor IP cores now use wishbone bus. This is similar to the AXI bus or the AHB bus found in Xilinx and ARM system on chips designs, and it provides a standard system on chip interconnect just like those. I won't go into much detail, but wishbone bus is a great example of open source technology benefiting everybody. Another benefit, one that we use quite heavily in OpenRISC development, is continuous integration. Well, what's that? Continuous integration is where when you commit your code into your GitHub repo, if you're not using version control, I suggest you try GitHub. You submit your code into there, and as soon as it's submitted, you can run tests on it. So if you have Vivado or Quartus, those tests might be, running those tests might be an involved process. It might be very difficult to install those tool chains up onto the cloud because you need licenses, because you need to have 20 gigabytes of installation. So using open source tools means that we can run full simulations of our Verilog code and also do formal verification all in the cloud with open source tools, and it's not 20 gigabytes. You might have 20 megabytes. And that gives you lots of confidence while you're developing your code, and you get quick feedback. Another tool that helps you build software is FuseSOC. So in the software world, if you want to build your software, you have GCC, Make, and Gradle. You can get your different software from PyPy, from NPM. For Java, you can go to Maven Central. And just to get binaries or libraries on the Unix machines, you can use apt-get or yum. In the hardware world, this doesn't exist. You usually have to either download a core from a vendor, or you copy your cores around into your different projects, and you have a proprietary Quartus or Vivado system to build your tools. FuseSOC solves those problems for the hardware world. You have core repositories which can exist on Git or just on your local file system, a shared file system, where you can import into a single design multiple CPU cores, SD-RAM cores, USB or audio cores, any types of IP cores that you need. You can import them, and FuseSOC takes care of building them. And the nice thing is that it can retarget a design for Xilinx, Intel, bitstreams, FPGAs, or it can also produce a simulator, all with the same design file. Let's look at a demo. So with FuseSOC, let me start off with, in this demo, we're going to compile a program and run it on our OpenRISC core. The prerequisites is that you have a compiler you can download from here, and you need to install FuseSOC, and then you're ready to go. Everything else will get either directly from this demo file folder, or we'll just download it directly from the internet. Well, these are locally stored, but they've just come from the internet. So first off, we use our compiler to compile our Hello World program. Next is FuseSOC. So let's import several cores into our FuseSOC library. But first, if you look at our FuseSOC system, we can see that by default it has imported a few libraries for us from the web. Now these provide things like the SD-RAM controllers, RAM simulators, and other things. You can look into that. Next, let's import the More 1KX CPU. But before that we do that, let's just check out what is this core. So the core is just your directory with your Verilog code in it, and what makes it a FuseSOC core is that it has a file called the .core file that has a list of basically all of the Verilog code that should be imported if you want to download this and import it. Now this can be downloaded from an external repo like Git or a website, or it can be just a local file. In this case, I have a local Git repo, so I'm just importing that directly. So let's import all of these cores. Let's also import this IntGen core. Now this one is coming from Git. We can see when we import that, it downloads it from Git. And next we want to run it. So here, now this one is coming from Git. We can see when we import that, it downloads it from Git. And next we want to run it. So here we're going to run a simulator. We'll build a simulator actually and run it. So it's going to build an Icarus, an iVerilog simulator. This is just the type of top level project inside of the More1KX system on chip we want to run. And we say we want to load using ELF loader, our binary, and it will place that in memory. Now once we run that, we also specify a VCD file. Once we run that, we can see that the simulator was generated, it loaded our ELF binary, and our Hello World program runs. Hello COSCUP 2021. Now the last argument we did there specified VCD, and what that does is that creates a waveform file that allows us to debug our design. Now, in the open source world, we have GTK Wave, which is a great tool for looking at our waveforms. So let's open up our waveform. So we can see here we have, this is the file we've just generated. We can load that up, and when you load up your waveform, what you can see on the left is just a list of all your signals, and so you can take these signals and import them into your waveform viewer over here on the right, and you can see what's going on. Now that might be a bit tedious, so I suggest you use a save file. So I can load up a save file, which I have here stored, More1KX pipeline. This I've put together earlier, and it allows you to investigate what's going on in your program on the CPU. So here we can step through the instructions that are executed, and we can see how they come in through the fetch, decode, execute, reading from the register file, the ALU, whether it's ready to move on or whatever, and writing back to the register file. Alright, so GTK Wave is a great tool. Back to our presentation, and another demo coming up. So the next thing we're going to look at is formal verification. So if you have IP cores and you want to prove that they're ready for production, one of the steps you might use is formal verification. This allows you to prove that no bad state can ever enter into your hardware. And the tool that we use to do this is called Yosis. A high-level tool for this is called Symbiosis. It's a Python wrapper around Yosis that allows us to do formal verification. But what is Yosis? Yosis provides synthesis for Verilog design. So basically you have your Verilog, it's a compiler, and it will generate a netlist. And that netlist can then be loaded into an FPGA after you do place and route. But another thing it does is it also provides a way to create a SAT model and send your design to a SAT solver. What is a SAT solver? We'll look at that a little bit later, but that allows you to do formal verification. So Yosis was designed by and coded by Claire Zen, and it's an excellent project, and Claire is a rock star developer in the open source silicon world. With formal verification, what you can add to Verilog is these keywords: assume, assert, and cover. We'll look at those a little bit later, but basically these allow you to constrain your system to say what are the possible states that this system can get into. And what the SAT solver does is a satisfiability module theories, SAT for short, or SMT for short. What it does is it basically, with a constrained system, it will be able to tell if your design can go outside of the possible good states, basically. And when we run Yosis we can actually go into two different states. I mean, when we run Yosis, it will solve us our design using, it will do the formal verification solution to our design using two steps. One is the bounded model check, and the other is the K induction. So bounded model starts in a good state and tries to go into a bad state, and K induction starts in a bad state and works backwards to try to see if that bad state can be entered into. There's some great tutorials on the internet, so I suggest you check those out. So this year, as part of the Google Summer of Code project, we're adding formal verification to more 1KX. So that will make it a more trustworthy CPU and IP core. Harshita is helping us with this project, and you can follow her on Twitter. Let's do a quick demo to see how this works. So with formal verification, if we look at one of our design files, we can check out what's going on here. So we have our store buffer, which is basically a FIFO. At the end of our design, we have the formal section. So this section is only used if we're running formal verification. There's an if-def there to block this off if we're not doing formal verification. And what we can see is things like, we can check after we reset, assert that the state becomes empty. So the FIFO is empty after a reset. And if it's empty, it should not be full. Now, let's say we got this wrong, or there's a problem in our code, and we wanted to check if our formal verification works. So let's run this right now. So we do make C formal bench formal, and we will run our more 1KX store buffer test. And what we can see here is we run two types of checks. One is the BMC, which is the base case, and one is the induction. And we can see that we have a failure here in the base case. So this is the BMC. So it means that from our initial state, we've got into a bad state. And we've outputted a waveform that shows that bad state. Now, we can load that waveform up into GTK wave, but basically we know the problem that when we start our system, full should be false after a reset. So if we change that back to asserting that full is false on a reset, and we run, we can see that the base case, it steps to 29 different cases, and it cannot find a failure in our assertions, so it passes us. Done. Now we can add many assertions and many assumptions to our design, and this is what formal verification is. So, wrapping up, if you want to know more, I'm part of the FuseSOC Foundation, and we help support free and open source silicon, from front-end design, back-end design, to fabrication. And you can check out our conferences at ORConf and LatchUp. These are held yearly. ORConf is in Europe, and LatchUp is over in America. Thanks a lot, and let me know if you have any questions.
Hi, Stafford. Can you hear
Hello.
me?
Yeah, I can hear you.
Oh, sorry. Oh, I need to volume down. Okay, so here are the questions. So, although it's all asked by me, I don't know why.
Okay.
But anyway, yeah, I'm curious that will there be SMP support for MOR1KX? If memory serves me correctly, I believe yeah.
Yes, so basically SMP support came into more ONKX and OpenRISC architecture probably 5 years ago when I started the project. So I noticed actually the presentation title that was on COSCUP mentioned about more 1KX and SMP, but that's actually quite old news. So I'm not talking about that today, but yeah, it's there. So we added that to the architecture. There's some, it doesn't have like a cache interconnect like most CPUs do. We use bus snooping, memory bus snooping to invalidate caches. So that's kind of one of the complicated things. And then there's a new register that tells the CPU core ID for each CPU. There's a module for inter-processor interrupt communication, and that's been implemented in the architecture, like I said, probably 4 or 5 years ago. But then one of my first projects in this OpenRISC was actually getting the SMP support upstream into Linux. So that's in Linux now. So you could build a core from the same DO Nano, and you can run 2 more 1KXs on it and boot Linux with SMP support. That was, yeah, like I said, a few years ago, but it's there.
I see. There are new questions, and I think we should answer them first. How many bugs have formal verification caught during development?
So the formal verification, we found a few bugs. Mainly, it's around really tight instruction cases which don't really happen in the real world, but we've been able to fix. So, for example, if you do 2 cache invalidations of the same cache address right away, those are called SPR instructions, special purpose register writes. And usually you won't do that. You won't invalidate the same address, but that caused, but basically formal picked that up, that we don't detect the second or some, I can't remember. We don't detect that it gets done right away, and we can actually miss the cache invalidation. So those are things that it's found. It doesn't really happen in the real world, but it's something we've been able to fix without adding. I mean, one of the things that's kind of a different topic, but kind of a balancing act for formal verification is, should we make it perfectly right, or should we add a lot of logic to the core? If it's something that, this should never happen, we don't want to add, 20 more steps to the pipeline or something or 20 more registers, because we want to try to keep our system pretty efficient so we can change our formal verification. But in that case, it was something we could fix without, we can actually simplify the design and make it, just as performant, or not taking too many extra resources. Yes. And then you want to ask the question and I can answer, or it's nice. How does System Verilog SVA compare with Yosys formal verification, assume, assert, cover? Are they the same thing? I don't know. System Verilog SVA, I don't know what that is. Maybe it's the same thing, possibly. System Verilog attributes, I think I've heard of that before, but I believe it's the same thing, and maybe formal verification is just bringing that into Verilog, but I don't know. And then the next question is about SMP support, and next question is, will OR1KX revive dev heat of OR1KX?
Oh, sorry. I misspelled it, and I have accidentally turned my mic off. Yeah, this is, I'm not trying to be harsh, but since the RISC-V came out of a place that OpenRISC is some kind of being drawing out the development power. So will MOR1KX become revive the development heat? Or
I don't think so, really. To tell the truth, More 1KX has been around probably since 2006, so quite a bit of time before RISC-V. So it's not going to take over RISC-V. But I think in OpenRISC, kind of the thing that's good about it is it's quite simple. It's not changing a lot. It's a small architecture. So RISC-V is, they have lots of extensions, the 64-bit. But with OpenRISC, it's kind of, I wouldn't say hobby, it's production quality, but it's in a place where it's a small community and you can still find, it's very mature. And so you can get in there and make changes and make suggestions, and you can continue to use it. I think it's just kind of niche with the RISC-V, being so commercial now, but I don't think so. But my point is, it's just OpenRISC is nice because it's pretty simple and it's easy to understand the whole architecture, and there's lots of things to still work on there. I think some people like it because it's quite simple, mainly 32-bit.
Okay, I see. I think we can a little bit stretch the deadline of our session, so maybe you can answer these last two questions.
Okay. In your opinion, while applying formal verification flow into development, what is a good flow to do, like tested? I think it's basically adding formal into your development is just like test-driven development. The nice thing about formal is it's kind of like writing unit tests. With unit tests, though, you have to drive your design to the states you want to go to. With formal, you can just say the state you want to go to, and the formal verification figures out how to get there. So it can cover, cache invalidations, or cover, MMU lookups and things like that with quite simple logic. And it's pretty neat how the solver can test your logic. So yeah, I think it should be a part of test-driven development, and that's what we're using it for now. It's integrated into the More 1KX CI pipeline. So whenever you commit code now, formal verification will run, and we'll be sure that we don't break any assertions and assumptions, which is great. And then, okay, next question: any suggestion for open silicon hardware startup? I'm not a business person, but I think, if you just keep doing the right thing, I mean, if you provide solutions for, designing hardware and designing the software that goes on it, as you know, like designing the hardware is pretty complicated, but the whole software stacks to do the compiler, the operating systems, it takes a lot of time and effort. So if you're an expert in that and you can, bring new hardware to a solution, you can do consulting or something like that. I think there's lots of people who want that, and I wouldn't say do it in OpenRISC or do it in my processor, but RISC, you should be able to do it on anything. So RISC-V, ARM, if you want to do, I'm saying if you want to do business, providing solutions for all of these types of processors and knowing how the hardware works and how the software works is always marketable for a startup or for any kind of business, I think. Yeah.
Thanks a lot. Stafford, I'm a little bit curious. If this is too intrusive, then just to tell me bluntly that you cannot answer this question. I'm curious that are you working full-time for this kind of open source CPU development, or you're doing it in the hobby time?
No, this is my hobby. So actually, I work at a bank and I work on trading systems. And I don't know if you know, but banks and trading systems have been getting more involved in FPGA development and high frequency trading. I don't work on that yet, but it has been beneficial for me knowing this kind of low-level stuff, because whenever you start to look at performance problems of any computer systems, the more you know, whether it's to low-level caching or how the OS works, or how SMP works, the better. So this has been my training tool, and that's the one thing about OpenRISC is it's a great training tool. So anybody who wants to get involved and build this stuff, contributing to this or any open source project is a great training tool to build up your skills and knowledge. Maybe someday this could be my work.
I feel the urge to ask one question.
Yeah.
Why did you pick OpenRISC instead of some kind of maybe Super Edge? You know that Super Edge is being recreated by, I believe, the developer is also lived in Japan. That is Jeff. You know the creator of Music Linux and the creator of BusyBox are collaborating to re-implement the Super Edge. Josh just said, yeah.
Yes. Super H, yeah. No, I've met those guys. They're my friends. They work here in Japan. I met them after I started on OpenRISC, so that's kind of why I didn't get involved in that. Also, the guy who does, I don't know if you mentioned, but Muscle?
Yeah, MULCL, yeah, Muscle, the Muscle Literacy.
Yeah, yep, those guys, I know them, and they're doing a good job. I guess they didn't ask me for help. They've been pretty quiet since I talked to them, actually. But yeah, I mean, the reason I started with OpenRISC is the same reason you did. I got that DO Nano. I was an FPGA developer out of university, and I wanted to keep doing it because I thought it was so cool. So I got the DO Nano, and I started to build a bunch of IP cores. But at the same time, I was an open source, like Linux guy, and I thought, well, I have all these IP cores I'm writing myself, but what's the open source community have? So I searched the internet and I found, oh yeah, you can run OpenRISC and Linux on this DO Nano, and I did that. And then I found some bugs and I fixed it, and I started talking to the guys, and they're like, well, can you do this, like port GDB to the OpenRISC? And I was like, well, I can. I mean, they had a port, but can you help us fix it up? And I helped with that, and then I helped with another thing, and now I'm kind of one of the main people. So yeah, that's how I got involved, and it was just always fun. There's always new things to work on.
Because you mentioned the toolchain issue, I'm curious that why the old OpenRISC toolchain was kind of abandoned, and without you, the OpenRISC will kind of be deserted in the desert. So what happened back then? Why did they cannot get mainlined?
Well, I'm not sure. There were some political things before my time. I think there was, I don't know too much about it. I think there was some political things.
Issue. Yeah.
Well, yeah, with the GCC, there was a copyright assignment issue, and people thought it was dead, that we couldn't get GCC upstream. So that really hurts the progress of the tool chain. But I actually just said, oh, I'll rewrite it from scratch. So I rewrote the whole GCC from scratch, and we got that upstreamed. And so now it's actually, there's no real things locking it down. I think RISC-V on the other hand has done pretty well with how they design the architecture. So they've looked at things that are wrong in the OpenRISC architecture itself, like the extensions and the compressor or the dynamic size instructions. RISC-V doesn't, or OpenRISC doesn't have any of that. So they've done some really neat things that make it more modern instruction set architecture. But I think OpenRISC, if you just need something simple, it still is there. And those political things are not there to hurt it anymore, I think.
Okay, thank you so much. And thank you for answering so many questions. Then
no
we
problem.
will, yeah, okay, then just saying bye-bye and
Bye.
ありがとうございます。
はい、どうもありがとうございます。谢谢。
Yeah.